Hello there, Philip here with my own puzzle Krop Kages 2 that I intend to solve on video, just to record the intended solve path, maybe show it to the solvers and let them see whether or not they found the intended logic. And I will show you the puzzle. A small word before I start. This is the second Krop Kages puzzle I have done. I've done one almost a year ago, and it's rather similar, or this one is rather similar to the first one, in that it is quite tricky to break into this puzzle, and then it uses the logic of Kropki, Kages, and especially the negative constraint to solve. And it's been in my head for a while, this puzzle, and while setting it, I intended to smooth out the solving path, especially after the break-in, and just make it more enjoyable. And I think that this turned out very well, this puzzle. I like it more than the first one, and I will try to show you how it's intended to be solved. But before I do that, I will just go through the rules real quick. So we have standard Sudoku rules apply. That's obvious. Then we have standard killer Sudoku rules apply, but we have no cage totals. So you can see already we have cages in the grid. And these are standard killer cages, except we don't know the killer sum yet, and we have to deduce it ourselves. One exception is this cage here. It's a big cage of 16 cells, and this is defined to be balanced in a way that it has to have at least one of every digit and not more than two of every digit. So basically you have to complete one set of 1 to 9 before you can start the second set and so forth, but there's only room for one and some, not for more than two sets. Next rule, Kropki rules do not apply to cells. So if you're familiar with Kropki dots, we have white dots and black dots usually in Kropkis, and black dots show a 1 to 2 ratio between the value of the cells, and white dots show that the cells connected are consecutive. But this does not apply in this puzzle, so we don't have the same relationship necessarily for the cells connected with a dot. These dots that are shown in the grid rather connect the cages, so the rules for Kropki just apply to the cage totals. In this case, these are singular cages, so it works just the same, but right here you can see that between this 3-cell cage and this 1-cell cage there has to be a 1 to 2 relationship because of the black dot. But this does not mean that this cell right here has to be in a 1 to 2 relationship with that cell. Also, we have gray dots in the grid. Gray dots in the grid are just standard Kropki dots basically, but we do not yet know whether or not it's a black dot or a white dot. So during our solve, we have to find out, is this a black dot or is this a white dot? At least we know there's a Kropki relationship between those two cages. Now we also have another special Kropki dot, which is right here, because it's not between 2 cages, but between 4 cages. And the rule right here is just that diagonally adjacent cages have to follow this Kropki rule. There's no Kropki relationship between these two cages unless otherwise stated in another cell, but these do not necessarily have to be in a 1 to 2 or consecutive relationship, but these diagonal cages have to be, and these diagonal cages have to be. Now, another rule is obviously, because we have multiple relationships, they have to be the same relationship. So if one of this can be shown, oh yeah, we need a black dot between these two cages, then obviously these two cages would need a black dot as well. If this was a white dot relationship, this would have to be a white dot as well. And then the final rule, and a very important one, is all possible dots are given. And this is just a negative constraint on the dots and will be important in the solve later on. So yeah, it's taken me 5 minutes to explain the rules, but I think they're fairly clear. It's just that not everyone is used to applying the Krop key rules to the cages. But what's also taken a little bit of time is explaining two special rules, which is this big cage, killer cage that is more than 9 cells big, and also this diagonal Krop key dot. And this will hopefully show you that this is very important to this puzzle, and also, yeah, the basics to the idea behind the puzzle. So obviously, I would not use this rule which I basically define for one cage only, or one case only, and here for one cage only, if it wasn't really necessary. And it's really necessary because both of these rules are important in the break-in to this puzzle. So the break-in in this puzzle is hopefully also a little foreshadowed, I don't know which how to call it exactly, by the color of the Krop key dots, because most of the dots that are gray can't really be disambiguated early on. So this should be a hint as to where to start. So we have a couple of Krop key dots up here that that are already given. The color is already given, and it shows the relationship between those cages, and that might show where to start in this grid. But first, we want to look at this big cage and what this cage means. So I've talked about this in the rules real quick, that this cage has to have at least one of every digit, 1 through 9, so we have 45 at least in this cage. And then there's, because it's a 16 cage, there's 7 digits left, and these have to be from 1 through 9 as well. And then we miss 2 digits. So basically, this is a cage that sums to 90 minus 2 digits that are missing. And these have to be different digits, because otherwise one set of 1 through 9 would be incomplete in here. Or both sets would be incomplete, which wouldn't work. So already from the very start, we have a restriction going on in this case. And this is, we can limit the sum of this cage to at maximum 87, which would be the case if the 1 and the 2 are missing. So we would miss 3, 90 minus 3 is 87. And if we miss an 8 and a 9, then we would miss 17. So the minimum this cage sums up to is 73. This is just where we start thinking about the logic. And the next one is thinking about this dot right here. So basically, we know what the big cage has to be, and we know that this cage cannot be more than 45 because it's a 7-cell cage. It actually can't be more than 42. So we immediately can tell that this dot cannot be a consecutive dot. It has to be a black dot, showing that these cells, or these cages rather, are in a 1 to 2 relationship. This also means that this cage right here will be half of this cage up here. And this means that this cell, or this cage up here, will have an even sum. And we just said that the range of possible killer sums in this cage is 73 to 87. So now we know it's 74 to 86, basically. If this is 74 to 86, and this is half of it, then obviously this run right here would be 37 to 43. Just keep that in mind for now. Now, one thing I also want to look at is how do these two cages interact except for this Krop key dot. So maybe if you've solved one of my previous puzzles, you've seen this already, but yeah, you could have already seen it in another puzzle as well. What this right here, this cage is also the the central cells of a set. So if you're familiar with set equivalence theory, then you probably know of Fistomefel and art. But in this case, it's not quite a different one. I mean, it's different. It uses different cells, but it's the same logic basically. So for Fistomefel, you use obviously different rows and columns, but if you use these four columns right here and these four rows right here, then you are left with basically the same logic on these cells. So set equivalence theory shows that blue colored cells have to be the exact same digits as the green colored cells. Obviously, because summing up four columns and four rows is 8 times 45. Also, everything except box 7 is also 8 times 45. And if we sum up these rows and columns, we sum up the blue square twice and leave out the green. But obviously, in the sum, they have to be equal. So I think this is fairly easy to see that blue and green are the exact same digits. And this is the idea behind this puzzle, because obviously we have this relationship given by set theory and we have another relationship given by our Krop key dot. And we want to use this to break into this puzzle. And for this to work, we have to understand how we can work with these other green cells around here. The first thing we note is that blue now has to be the same as green, and this blue was also twice this cage down here. So basically, these cages right here have to sum to the same as the 7-cell cage down here, and obviously have to sum to half of the blue cage. This is the first thing we notice, and then we want to find out how can we show, or how can we use this information? How can we calculate something with these cells? And here it's where we have to look at the Krop key clues in the top right corner. The first thing we want to look at is what do the white circles mean? Basically, whatever we put in the corner, we have a consecutive dot to here and here, which means we need the digit that is one smaller, the digit that is one bigger, and we need both of them in this case, in this cage. So we will always have two cells right here. One is bigger than this cell in the corner, and one smaller than the cell in the corner. Now we have the black Krop key dots, and we have to look at what this means for either the row or the column. And what we look at is the size of the cages. So this cage is a 3-cell cage, so it is at least 6. The sum of this cage is at least 6. And this shows us that the relationship from this Krop dot can never be in a way that this this cage is half of this cage. Because as this is at least 6, this cell would have to be at least 12, which is obviously not possible. So we learn for both of these Krop dots that the 1-cell cage is half of the 3-cell cage. And this already is enough to find out a relationship between these green cells, because as I just told you, let's just make an example. If we place a 5 in here, let's just stay in the middle, then we would have to have a consecutive digit here, which would be a 4 or a 6. And obviously right here, if it's a 4 in this cell, then we would need an 8 cage. If it's a 6, we would need a 12 cage. So we have 2 options. But also down here, we have 2 options, and these are the same options. So we have a 4 and a 6 in this cell, and then we would need an 8 cage or a 12 cage in this cell. Now, what you can now see is we have 2 options on both sides, but we need both options at the same time, because these 2 cells obviously can't be equal to each other. So one of these cages will be a 4 in this case with an 8 cage, and the other will be a 6 with a 12 cage. So what we learn from that is, if we know the digit that is in the corner, then we know what these 2 digits are, and we know what these 2 cages are, at least summed up. And this in turn means that we already know what these 4-cell cages down here and up here are. So we learn that there's a relationship between the digit in this cell and the sum of these green cells around here. And we want to find out how we can describe this relationship. For this, I will start in a different way, and I will start by adding up this row and this column. So hopefully you can see that when we sum up this row and this column, and we sum up 45 times 2, then we are left with 90. So we are left with 90, but we counted this cell in the corner twice. And now we want to take out basically these white cells and this corner cell once, so we are left with just these green cells. And we can do that actually, because we can show what is the sum of these white cells in relationship to this green cell up here. So let's make this a red cell real quick and think about what this means. So let's also call this X, just for me to make it easier to explain this. So we have 2 cells next to this red cell that have to be consecutive. We already learned that one has to be bigger, one has to be smaller, but we also know that if we sum these 2 cells, we always get 2 times X, so 2 times the red cell. Obviously, now if we double what is in this cell and we double what is in this cell to get the 3-cell cages, we also can sum these up, and we are left with 2 times the value of these 2 cells, which was 2x. So we have 4x in these 2 cells, then 2x in these 2 cells, and 1x obviously in the corner. So if we make all of this red, we are left with 7 times what is in this corner cell. And this already is enough to show the relationship between this corner cell and the green 4-cell cages right here, because I have just told you that when we sum up row 1 and column 9, we want to get rid of the formerly white cages and 1 time the corner cell, and then we are left with the green cages. And what we want to get rid of is just the red region here, and we just showed that is 7 times what is in the corner. So if we sum up row 1, column 9, and which is 90, and we subtract 7 times x, then we are exactly left with the sum of these cells that are now green. And this is the breaking into this puzzle, because now we can compare this to what are the options for this cage down here. Because this 7 cell cage, we already talked about, this is the same as these 9 cells here. And we just go through the options. So what can be in this cage up here? We could, for example, put in a 6. So if there's a 6 up here, then what would be the sum of these green cells? We already talked about this. It's 90 minus 7 times the cell, which would be 42. 90 minus 42 is 48. So we would be left with 48 in this cage down here. Obviously, this doesn't work. Now we can put in a 7. So what would the sum of this cage down here be? In this case, we would have 90 minus 7 times 7, which is 49. So we would be left with 41. This sounds good. And let's just check. If we put in an 8 up here, then the green cells would add up to 90 minus 7 times 8, which is 56. So it would add up to 34. This doesn't work as well. So we would basically be left with the 7 in this corner and a 41 in this cage down here. Now, you may wonder, why did I rule out the 6 and the 8? What was the reason behind this? Obviously, we have written down or memorized from earlier in the video that the possible options for this cage were 37 to 43. And only by putting a 7 up here, we are hitting this range for the cell. So yeah, it's taken me basically 20 minutes or 15 after the explanation of the rules to explain this break-in, but I hope it was fairly clear. And I hope that it's also something that you could possibly find out yourself. I hope you found the set, and but I think when the set logic is clear, then the calculations are fairly trivial after that. So now when we find out that this is a 7, we can actually go on and pencil mark some more, because we have a 6 and an 8. And we want to find out what's in these cages around here. So we learn from this being a 7 that the cage down here has to be a 41 cage. 41 cage in 9 cells basically needs all the digits except for 2 digits that sum up to 4. These are the digits 1 and 3, so we take out the 1 and the 3. So now we have a 1 and a 3 missing from here, but we have all the other digits. Now we can also work with what I talked about when I explained the set. We know that blue and green do not just have the same sum, but they also have the same digits. So we can use this to determine which digits have to be right around here. So to use this, we want to first determine what would be the direction of these two cages. So which one is the 6 cage and which one is the 8 cage. So we already know what are the sums for these cages around here. And to do this, I will calculate what is the value of these green cells around here. So in one of these cases, we have a 6 next to the 7, so we would have a 12 next to it, 12 cage next to it, and we would be left with so we have 12 in here, and then 6 and 7 is 13, which would sum up to 25 in total. So we are left with a 20 cage. And if this is an 8, then we have 15 already here. We have 16 in this cage, 15 and 16 would be 31. So we would be left with a 14 cage round here. Now, this is a little tricky again, this next step, but what do we have to work with? We have 2 crop key dots on this green cage down here that might help us determining the direction of these cells up here, or the order of these cells. So this is probably the one more helpful because it has a very big cage attached to it. And we now know that this green cell either is a 14 or a 20. And we also know that this cage right here has 7 cells, so it is at least 28 if we sum up the digits 1 through 7. And this also means that this relationship here can't be a white dot. So if we have 14 or 20 here, we could never have a consecutive relationship. This means we have a black dot right here, and we want to use this black dot. We know that the 7 cage is obviously bigger than what is in here. And what are the options now? If this is a 14 cage, this would have to be a 28. And if this is a 20 cage, this would have to be a 40. So looking at this, you might think, yeah, both of these are possible. If we use 1 through 7, then this would be in 28 cage. If we leave out 2 digits that sum to 5, then we have a 40 cage. But this is the first time that the negative constraint comes into play because we have a 41 cage down here. So this 41 cage obviously can't be next to a 40 cage without needing a consecutive dot or a gray dot in this case. So this right here cannot be the 20 cage, or this would be a 40 cage and we would need a crop key dot. So this way we can show that right here we need the 14 cage, giving us a 8 right here and the 16 here, and then the 14 cage there. And we are left with a 6 here, a 12 here, and a 20 cage up here. Now we want to continue where I stopped earlier. We want to find out what digits could be in these 4 cell cages, and yeah, in the same way, what digits can be in the 3 cell cages here. So we think about this cage maybe first. We do need 16 in this cage, and we have a 7 and an 8 already in the column. So if we do not use a 9 in this case, then the maximum we could put in these cells would be 4, 5, and 6, summing to 15, which would not be 16, obviously. So we definitely need a 9 in this cage. And now we use the relationship I talked about earlier. We know that blue has the exact same digits as green. And we also know in blue that we sum to 82, missing 2 digits that sum to 8. So we definitely need 2 9s. There is 1 9 in this cage down here. There is a 9 here, which means there can't be a 9 in this 4 cell cage. So we definitely need a 9 in this 4 cell cage. So I'm going to put in a 9 up here. Now we also know that we need a second 8 because there can't be an 8 missing from this blue cage. One of the 8s is in this cage down here. Right here we cannot have an 8 because there's an 8 already in the column. So we need an 8 also in this cage up here. So now we have an 8 and a 9 in this cage. We know it's a 20 cage because of the 6. And how do we get to 20 with an 8 or a 9? It has to be 1, 2, 8, and 9. So the first thing this gives us is also this 12 cage, which is now a 3, 4, 5. But it also gives us a second 2. So we realize we have a 2 in this cage, we have a 2 in this cage, which means we cannot be missing 2 and 6 from this cage here in the middle. So we are either missing a 1 and a 7, a 2 and a 6, or a 3 and a 5. We cannot be missing the 2 and the 6 because we have two 2s already. We also have a 7 up here and the 7 down here already, which means we can't be missing a 1 and a 7 as well. So the only option for this cage is to be missing a 3 and a 5. So we have every digit from 1 to 9 twice, except for the 3 and the 5, which obviously can only be in the green cells once now as well. So we know it's 3 and 5 are only once in the blue cages, in the blue cells, so they're only once in the green cells. 3 and 5 are not in these cells. 5 is down here, but the 3 is not in here, so we definitely know there needs to be a 3 in this cage. Now we continue with the 6. We know that there's 2 6s in the blue cage, and we only have 1 6 so far because we have 1 6 down here, but no 6 in row 1. So there needs to be a 6 in this cage as well. And then we think about how can we make this cell or this cage, these cells add up to 16. So we have a 9 already, so we need 7 still to make this a 16 cage. We cannot use 6 and 1 because the 6 is already down here. We cannot use 3, 4 because the 3 is already down here. So this has to be 9, 5, and 2. And down here, we are left with 3, 4, 1, and 6. So right now we have deduced the digits for every cell that was used in the break-in. We already know what digits have to be in the blue cage, but we won't put them in already because that would be too many pencil marks. All right, so what did we find out? We did find out that this right here is a 14 cage, and this is a black dot, so this actually is the 28 cage, and we can fill in the digits for this cage because they have all the digits from 1 to 7. Now we already know that this is a black dot right here, so by using the black dot relationship on the other diagonal, knowing this is a 28 cage and this right here can't be a 56 cage, we know that this has to be a 14 cage. And knowing that this has to be a 14 cage, this dot right here can't really be a consecutive a white dot because we can't put 13 or 15 in one cell, so it has to be a black Krop dot 1 to 2 relationship. 14 in this cell needs a 7 in this cell. We now know that this right here has to be a 14 because there's a black dot, so we have a 1 to 2 relationship, and we can't use half of 7, so this is a 14, leaving us with only 9, 5 or 8, 6. And then we have a gray Krop dot, which I think we cannot yet determine. We have a 14 right here. This could be 13, 15, or 7. So nothing we can put in right here. Now let's think about this 14 cage for a second. 14 in 4 cells is an interesting number because it's the minimum that you can make this cell, this cage add up to if you do not have a 1. So looking at the column, we can't put a 1 in this cage down here. There's only one option, and we can take a look at this. So if the 1 is in this cell right here, we would be left with what is 2, 3, 4, and 5 in this cage, as the only option to make 14, and then we would have 6, 7, 8, or 9 down here. And now we can think, is this possible or is it not? And to find out, we have to actually look at the different row in the grid, because we just placed these digits right here in the 28 cage, which are 1 through 7, do not use an 8 or a 9. We know that this cell right here cannot be an 8 or a 9, so we definitely need 8 and 9 in these 4 cells. Which means if these 4 cells have to include 8 and 9, then in this cage we can't have 8 or 9 down here in this cage, and we can take these pencil marks out. But looking back at the logic with the 14 cage now, if we put the 1 up here, put 2, 3, 4, and 5 in this cage, we would need an 8 and a 9 in the remaining 4 cells of this column, but we can only place them in one cell. So this does obviously not work, and we can take out the 1 from here and place the 1, not exactly, but at least as a pencil mark in this box. Yeah, not this box, in this cage. Also, you might realize that in the same column we do not yet have a 3. We can place this as well. 3 obviously is missing from this cage down here because we are missing 1 and 3, and 3 can't be in the 20 cage up here. So we learn that this right here has to be a 14 cage, and we know that 4 of these is already occupied by using the 1 and a 3, so we need another 10. And we can't use obviously a 1, 9 because we have the 1 already. We can't use a 3, 7 because we have the 3 is already. So we need either 2 and 8 or 4 and 6. Now I won't put these pencil marks in quite yet, or maybe I will. It's I think easier to see. So I put in a 1 and a 3 that are definitely in there, and then we have the 2, 8 and the 4, 6 as the only options to add to 10 in this cage. Now we want to look at what this cage down here implies, and what are the implications of this cage. So we know what is in these 3 cells. It is basically everything that is not in here and that is not a 1 or a 3. We know that there's a 1 and a 3 in these 4 cages, in these 4 cells. So whatever is not a 1 and a 3 in this 4 cells we just talked about, this is 4 and 6 or 2 and 8. And whatever is in this cell up here, these are the 3 cells that are missing from this cage down here and have to be in row 6 in this cage. So we definitely know that right here we either have 4 and 6 with this cell up here, or 2 and 8 with this cell up here. Another way to show is we do not have a 5 and a 7 right here. We need a 5 and a 7 down here, so 5 and 7 can't be in these 3 cells. Now, what I was hinting at, we definitely have either 4 and 6 or 2 and 8, which need to repeat in these 3 cells. In other words, we need at least either a 6 or an 8 in these 3 cells, meaning we can never have a 6, 8 in this cage to sum to 14. So we can take out the 6, 8 option for this cage, which gives us a 5, 9 pair to sum to 14. This 5, 9 pair actually resolves this 16 cage so far as to giving us 1 digit. So we get the 2 right here, which we can take out from some pencil marks, but that's basically all that happens over here. And we look back at what happens in this 41 cage down here. This 5 and 9 also eliminate the 9 from these 3 cells, putting the 9 in this cell. This is the only option for the 9 to go now in the whole cage. So we put the 9 in here, eliminating the 9 up here, and we think again about what can be in this cage. So we realized it's a 1 and a 3, and then either 2 plus 8 or 4 plus 6. But can it be 2 plus 8 now that there's a 2, 8 up here? Obviously it can't, so we can take out 2 and 8 from this 14 cage, and we can think about what this means for the column. We have a 4, 6 now in here, which means 4 and 6 can't be in here. We need a 4 and a 6 in here, definitely, but either now a 2 or an 8. We can tell by realizing we have a triple now, 2, 5, and 7. This is the only place the 8 can go. This will be the 8, and this can now only be a 4, 6, 8. So I'm going to put that in. So now we've got a lot of cleaning up to do with the pencil marks, because we cannot have a 4 and we cannot have a 6 in these cells right here. We cannot have a 4 and we cannot have a 6 in here. Also, we cannot have 2, 5, and 7 in these 3 cells. Now I think it's time to look at this cage again, where we cleaned up the pencil marks and try to understand what this means. So right here, we realize that we cannot have a 4 and we cannot not have a 6 in these 4 cells. This means that 4 and 6 are locked already in this column. This also means we can take out the 4 up here. But this also means that there's either a 1 or a 3 in these 3 cells, which would be the same that is also in this cell. Now, we also know that these 4 cells then obviously consist of 2, 5, and 7, and then the other one of 1 or 3 that is not in these cells. So what we are left with as options for these 3 cells now are obviously 8 and 9 that are missing from the 6 other cells in this cage and in this box, and then we need whatever is missing, 1 or 3 from these 4 cells. So this 1 or 3 in here is the same as the 1 in, or 3 in this cell, and whatever is in these 3 cells as a 1 or a 3 is the same as in these 4 cells, meaning obviously this can't be a 1 or 3 because that would clash. Now let's look how we can use this. So the first thing we might notice, we can clean up some more pencil marks, but we can also, by placing this 8, place pencil marks for the 8 in this cage up here. Yeah, it should be this pencil mark, but this helps us quite a lot, because earlier we talked about this. We know that this is a 14 cage, which would mean this could still be a 7 if this cage is black, but obviously it's now more than 7, so this can only be a white dot. Consecutive to 14 is 13 or 15. How do we make this consecutive to 13 or 15? Consecutive to 14. How do we make this add up to 13? By putting a 5. Adding up to 15 would be putting a 7. We can't put another 7 in here because we already have a 7. So we are left with a 5-8 pair summing to 13, being consecutive to the 14 cage. This 5 obviously points at this 5-9 pair over here, placing a 9 and a 5. I think they do not yield much more, other than we have a pointing 8 and 9 in these cells down here, meaning there can't be a 9 in this box right here. In these 3 cells, the 9 from here looks at this cell, so we can place a 9 in this cell. Now we can look at the 7. We have two 7s up here, do a little Sudoku once in a while, and place the 7 right here. We also know what these 3 cells are. We have everything except for 3, 4, and 6, which is lovely because we have a 1, 3, 4, and 6 cage right here. So we can take out the 1 and place a 1 right here. Now, as we know what these cells are, we can place the missing 2 digits, 2 and 5, in this row and take out the 5 pencil mark up here. This needs now 1, 3, and 5 as pencil marks. And right here, we are left with 2, I think, 3, 4, 5, and 6. 5 can't be in here because of this cage, but these should be the options so far. Now let's take a look where we can continue. We also found out that this is a 4, 6, 8 triple, leaving us with 4 digits in these 4 cells, which are 1, 2, 3, and 7. We know that this can't be a 7, so we can fill out the pencil marks. This can't be a 2 because of the 2 over here. Now I think we can look at these cells again. We just placed the pencil marks down in these cells and did not think about the implications of the cage borders, but we can do that for a second. So we have a 1 cell cage and a 2 cell cage right here, and we can look at the options for these 3 cells. One thing we can realize is that whenever we put the 6 in this cell right here, we would have a 3 and a 4 in the 2 cell cage, adding up to 7. But 7 and 6 would need a white dot or at least a gray dot to connect them, so the 6 can never be in this cage, and leaving this to be a 3 or a 4. This also means that the 6 has to be in the 2 cell cage, and if this is a 6 with a 3 or a 4, then we add up to either 9 or 10. And we think again, negative constraint, we have a 20 cage up here. We do not have a dot between the 20 cage and this cage, so this cannot be a 10 cage. So it can't be a 4 in this cage. It has to be a 4 over here. Take out the 6 pencil marks. This 4 gives us a little cleanup on the pencil marks down here, but as far as I can tell, we do not continue right here on this side. We want to use the same logic now, though, on the bottom left. So what can we work with here? We already know that this right here is a 14 cage, and we know that there's a gray dot connecting it to these cages right here, and we want to find out what that means. So this is a 14 cage. Looking at what this dot could be, can it be a black Krop key dot? In this case, it would be a 7 or a 28. 28 obviously doesn't work in less than 7 cells, so this can't be a 28. So it would be a 7. Can we place a 1, 6 in here? No, we can't, because we have a 6 already in the same box. Can we place a 3, 4 in here to make 7? We cannot, because we have a 4 already in the box. Can we place a 2, 5 in here to make 7? We cannot, because this would clash with the 2, 5 pair up here. So we realize this cannot be a 7, and it has to be consecutive to the 14 cage, meaning this is either a 13 or a 15. How do we make 13? How do we make 15? We can put in the options. but we can also I think look at somewhere else first, because there are quite a lot of options, I believe, for 13 and 15 still. You could make 9 and 6, 8 and 7 for 15, or the 13 would be 9 and 4, which would not work because yeah, let's put in the options. So if it's a 15, we cannot use 6 and 9 because the 6 is used in here. So if it's a 15, it would obviously be a 7 or an 8. And then if it's a 13, we do not use 4 and 9 because the 4 is already taken in the box. And we could use 5 and 8, so it could be a 5 with an 8. And we cannot use 6 and 7 because the 6 is already taken in the box. So that's correct. We actually have a limited options. We know that this is either 8 and 5 for 13 or 8 and 7 for 15, but it definitely needs an 8 in this box. In this cage, sorry. Now we think about what does this mean for the other cages down here. So if this is a 13 or a 15, we want to think, can this be black dots or white dots? So we obviously have an odd sum, so this can never be twice of what is in the other cells. Let's think about it the other way. If this is a 13 and we put in double that in the other cells, which would be at least 26, this won't work because we have 3 cells only. This can never sum to 26, so we can deduce that these two Krop key dots right here are definitely white dots, consecutive dots, and not black dots. Now, when we have a consecutive dot, what does this mean for these two cages? We have a 13 or a 15 right here. So the options are either 12 and 14 or 14 and 16. But we also notice we still have the 28 cage around here. So we can use the negative constraint again. We do not have a dot between the 28 cage and these cages, so they can never be a 14 cage, meaning they can only be a 12 cage in the case that this is a 13, or they can be a 16 in the case that this is a 15. This, however, is fairly restricted because 16 in a 2-cell cage would be a 9 and a 7. And I can place these digits to show you what I mean. If this cage is 8 and 7, and therefore a 15 cage, we need a 16 down here, which we could only do by placing the 9 here, the 7 here, clashing with the 7 we already placed in this 15 cage. So we realize that this can never be a 15 cage, and it needs to be the 13 cage. Having a 13 cage here with 8 and 5 cleans up some of the pencil marks because we now can put a 5 up here. And it also gives us the sum of these two cages because we have a 13 now in here and we can't make these cages add up to 14. These need to be 12 cages, so we can put a 1 in here, can place 3 and 9 in here, or combine the 8 with the 4 for a 12, but we already have a 4 in here, so this cannot be a 4 and 8. 3 and 9 pair, obviously we can take out 3 from these cells, but I believe that doesn't give us much more. Now we could go through the options of these cages, but I believe that we will be happier going another route, and that is finding out, do we have a 3 in here or do we have a 1 in here? Whichever is missing from these 3 cells will obviously be in here, and we want to find out which one it is. Now, how do we do that? We can take a look at what we do not have pencil marked so far and see if we can use it. So the first thing we realize, okay, we have placed a 7 here. Can take out the 7 pencil mark down here. 2 and 5 right here. Can take out the 5 pencil mark here and get a triple. 1, 3, and 7. Take out 1, 3, and 7 here. So we get a 2, 5 pair. This is nice because now we can reduce the options for these 4 cells. So where can the 1 go? We have actually nothing pointing at these cells, so we can place the 1 everywhere still. 2 is already in here. 3 can also be everywhere in this block, so we can place the 3 everywhere. But what are we left with now? We still need either a 4 or a 6 going everywhere again. 4 and 6. And we need a 7 and an 8. So now we realize, well, wait, we have a 7 pointing at these 2 cells, so the 7 has to be here. And we have an 8 from down here pointing at these 2 cells, so the 8 has to be here. So we go back, take out these pencil marks, and put in a 7, 8 pair in this case. Now, what do we now realize? These cells right here will be 1, 3, 4, 6, but as the 1 can't be in here, there definitely has to be a 1 in these 2 cells. So this one actually points down at these 3 cells and gives us what we desired, and that is the disambiguation. Is this a 1 or a 3? So we realize this has to be a 3, 8, 9 triple, taking out the 3 from all these cells up here. This 1 also means that there's a 1 now in here. Take out all these pencil marks, take out the 3 from here. We are left with the 1, 4, and 6 in here, which means this cannot be a 1 now. This has to be a 1, and we need a 1, or do it the long way. 1 can't be in these 3 cells. 3, 4, and 6 are taken. 1 has to be somewhere around here, but this now can't be the 3, which is what we were looking for. Can now disambiguate the 9, 3, and take out 3 from here. Now we look at these cells again. What are we missing in the box still? So we need a 1, a 2, and a 7 in the box to solve this. This cannot be a 2 because of the 2 up here. And we also know that this cage up here needs to sum to 12, because we know that this is a 13 cage. We need this to be consecutive. We can't have a 14. We need a 12. There's 8 and 9 already. We can never use the 7. And you guess it, the 7, 1, and 2 are disambiguated. 1 and 2 need the 9 to sum to 12. We need the 8 down here to sum to 15, which is obviously not in a 1 to 2 relationship or consecutive to the 28 cage, the 12 cage here, 12 cage here, or the 13 cage here, so there's no Krop key relationship around it. 7 also places 3 and the 7 in here. Then the 3 takes out the 3 from these cells and places 3, 1, and 4, places the 5, places the 3, takes out 3 from all of these cells, and obviously 5 places now the 5 and the 2. Looking at the rest of the column, 1, 4, 6 right here, takes out the 4 and the 6 here, so this is a 2. This can't be the 2 anymore, it's now a 4 and a 6. And we go back to this column, which is a 6 and 8 missing, which we cannot yet disambiguate, and we have a 3, 1, 2, 3, 4, 4 and a 9 missing here, which we can disambiguate because we have a 5, 9 pair here, just 4 here, 9 here. And these cells look back over here. This can't be 4, this can't be 4. And I think that is it so far. Now we use all the info we got down here and clean up pencil marks some more down there. 1 can't be in this cell, the 7 can't be here, 2 can't be in here, and what are we missing? Oh yeah, the 8 points right back here, 5 and 8, 5 and 7 actually take out the 5 as well from here, meaning that's the 2. This can't be a 2, 4, 5 and 7 left. 3 is already taken out from here, and I think that should be it. Now we can look finally at box 7, which was basically ignored for the complete solve so far, and we look at one row specifically where we have the most information. We have 4 digits already in this row, so what would be the options right here? We know we need a 1, a 3, a 4, a 6, and a 9 still in this row. So 1, 3, 4, 6, and 9. But we also know that there's a crop key dot in this row. And this crop key dot is still unknown. Is it a consecutive dot or a ratio dot? But we see fairly quickly that whatever this dot is, we cannot put a 9 on here. So if there's a 9 on here, it obviously can't be the black crop key dot because we can put 4.5 in a cell, and it cannot be consecutive because there's 8 already here. 9 and 8 doesn't work. So we can take out the 9, place 1 9, and disambiguate some more cells up here. Now we are left with only 4 options for these 2 cells, and we can think about, can then 1 be in this 2 cells? 1 needs a 2 in every case, if either with a black crop key dot or a white crop key dot. 2 is already taken, so the 1 can't be in these 2 cells. 1 actually has to be in column 5. Now we are left with 3 pencil marks only for these 2 cells. What does this mean now? We either need a white dot or a black dot relationship, and we realize it can only work if the 3 is in these 2 cells. So if this is a black dot, we need a 3 and a 6 to complete the crop key relationship, and if this is a white dot, we need the 3 and the 4. So the 3 can't be over here and has to be in this cell actually. Now we look at what is left in this box, and look at, okay, we can take out the pencil mark first from the 4. We're here, so this cannot be the 4. And we are left with 2 options for this cage and limited options for this cage down here. Let's first look at the row. What are the options for this row? We know we definitely need a 1, we definitely need a 2, and we need either a 5 or a 7. We have a 4-6 pair down here, giving us this quadruple. Now we are very limited in what we can place in these 2 cells, so we take a look. If this right here is a 3, then we would need either a 6, which would be 1 and 5, or we place a 2, which we cannot, and a 4, which we cannot. So this could not be a consecutive dot in this case. And let's place a 6 right here. Then what can we put down here? We either put a 5 or a 7. 5 would be impossible, and a 7 is also, no, it would work with 2 and 5. And if we want to double this 6 would need the 5 and the 7, which doesn't work obviously because we would break this cell over here. Or a 3 could be connected to the 6 with the black dot, which would need 1 and 2. So there's still quite a lot of options, but what can we take away from this? Is there a way to place a 7 in this cell? So if there's a 7 in here, we can never be consecutive to this digit anymore because we sum to at least 8. So we would need to be in a 2 to 1 relationship. Summing to 6 isn't enough, so we would need to sum to 12, and 12 doesn't work. Take out the 7 from here. Now there's options 1 and 2, placing 1 and 2 in here, which would be, no, before we look at this, we look at the column first. We have 5 and 7 pointing down here, taking out the 5 and 7 from this cell, placing a 5 or a 7 in here. We cannot use the 7, we just showed that this isn't possible. We need the 5 here. This is the only place for the 7 to go in the row. We place the 7, the 5, and a 5 in here. Now, we know that this is a 5, but we also know that this is a 1 or a 2. We have a 1 or a 2 already up here. Having a pair gives us a 3 in this cell. Taking out 3 pencil marks from here, placing this 3. This is also now a 6. This is also a 3. Take out some more pencil marks. And taking out the 3 down here, places this 3. Now we know that this has to be in a Krop relationship with the 3. It cannot be a 2, it cannot be a 4, so it has to be the 6 using the 1 and 5, placing 2 here, 1 here, and 2 here. Taking out the 2 from this cell and placing 1 and 5 down here. So just checking if we need to clean up some more pencil marks, but it looks good to me so far. And I think we can continue looking at the last cages we did not look at yet. And these obviously need a, looking at the row, we need an 8, we need a 7, and then either a 4 or a 6. So right now we can work with a 3 in this cell that does not have a relationship to this cell up here, so this definitely cannot be a 6. And we have a 4, 7, 8 still left. If this is a 4, this does not work because we have a 4 up here already. And yeah, let's take out the 7 pencil mark from the column real quick. Okay. We are now left with a 7 or an 8 in this cell and a gray Krop key dot to these 2 cells, and we need to figure out what are the options for this. So placing an 8 right here and having a consecutive dot would not work. Having an 8 would need a 7 or a 9, and we cannot make these two sum to 7 or 9. So placing an 8 in here would need a black Krop key dot, which would not be able to sum to 4, obviously, because we have too high of digits in here. We would then need to sum to 16. 16 is only possible with 7 and 9, which is not possible in this case, so we cannot place an 8 in the cell, and we place a 7. We can clean up quite a lot of pencil marks here, so I'm gonna do that. and we are now left with the decision to fill this cage next to a 7. Can we make it sum up to 6 or 8? Cannot, so this cannot be a white dot. It has to be a black Krop key dot, making this a 14 cage. With 4 and 6, there's only one. With 4, 8, and 6, there's only one way. Taking out the 4 with the 8 and 6, we can finish up this puzzle, placing a 4 in here. 8, 4. 6, and we're done. So obviously the timer doesn't stop. We can pause it manually, but then you won't see the grid. Timer doesn't stop because there are Krop key relationships that are not fulfilled. So basically the program thinks that there's still an error in here because I made an error, which would be an error using normal Krop key rules. But yeah, that's the reason why the timer doesn't stop. It still took me over an hour to go through the solve. So yeah, I definitely have to admit it's a pretty long solve, but I hope it's an enjoyable solve. And I hope you found some of the logic that was placed in this puzzle and that you enjoyed solving it. And with that, yeah, I think I won't make this video too long. Just hope you had a lot of fun with it. And yeah, see you around.